Hello students, welcome to EPG Pathshala. I am Dr. Abhilasha Shauri from Manav Rachna International University, Faridabad. Today we are going to talk on module HPLC mobile phase and delivery system under the paper chromatographic techniques. After completing this module, you should be able to understand about different types of mobile phases used in HPLC. To understand the principle of mobile phase selection on the basis of solvent nature, to learn about various components of mobile phase delivery system in HPLC, and to learn about effective delivery of mobile phase into the analytical column of HPLC. The mobile phase in liquid chromatography refers to the solvent that dissolves the analytes, separates them and elutes them out of the column at different time points. Separation of components in a sample occurs on the basis of different physicochemical interactions of analytes with the stationary and mobile phase. Solvent is continuously applied to the column and stationary phase for solubilization and elution of analytes. When the liquid mobile phase passes through the column, analyte molecules interact with the mobile phase and solubilize in it at different time points. This results into separation of sample components. These interactions, which occurs between the sample components, the stationary phase and mobile phase, are based on molecular size, as in size exclusion chromatography, on charge as in ion exchange chromatography, on hydrophobicity as in hydrophobic interaction chromatography, on specific binding interactions as in affinity chromatography, or it can be a combination of these. The mobile phase thus acts as a carrier phase for analytes. The component analytes elute from the column in a particular order, depending upon the relative strengths of their interaction with the stationary and the mobile phase. Nature of mobile phase. Mobile phase is a liquid solvent in liquid chromatography system, and it can be a gas in gas chromatography system. In liquid chromatography, it can be a polar or a non-polar solvent, or it can be an acidic or basic in nature, and so on. Commonly used HPLC mobile phases are water, aqueous buffers, organic solvents, or mixtures of organic solvents. While running the chromatography in an isocratic mode, the composition of the mobile phase is kept uniform throughout the analytical run, whereas while doing gradient elution, the mobile phase composition can be changed to obtain a pH gradient or a polarity gradient. Selection of mobile phases. The mobile phases are selected on the basis of type of chromatographic modes. In normal phase chromatography, non-polar solvents are used such as hexane, heptane, isooctane. The polarity is again adjusted by using slightly polar solvents like chloroform, isopropanol or ethyl acetate in its combination. In reverse phase chromatography, water is commonly used as the solvent. The polarity of mobile phase can similarly be adjusted by adding other polar solvents such as methanol, acetonitrile or tetrahydrofuran in mixed or varying ratio. For chromatographic separation and analysis of ionizable compounds, buffers and ion pairing reagents are added in the aqueous phase to increase retention. In ion exchange chromatography, aqueous salt solutions or buffers are used as mobile phase. Desorption of analyte molecules takes place by increasing the salt concentration in a gradient manner or altering the pH. Since the solute molecules carry charge and reversibly binds to the stationary phase by displacing the counter ions, they are eluted in the order of their strength of binding. The most weakly bound substance elute out first and vice versa. For size exclusion chromatography, the mobile phase is selected on the basis of its potential to dissolve the components of the sample and maintain its consistent viscosity at operating temperature. Ionic strength of the solvent is maintained by addition of salts. Highly polar solvents such as water, alcohol, acetone, etc. are not used with polystyrene column packings. Mobile phase and delivery system. The polarity of analyte molecules is altered by extent of ionization, and the molecules interact differently with solvent and counterions present in the bonded phase. For separation of ionizable analytes, the pH of mobile phase is adjusted to alter the degree of analyte ionization and consequently their polarity, which further alters the retention of analytes on the stationary phase. If the analyte contains an acidic functional group with pKa equal to 3, retention at 2 pH will be significantly greater because the analyte will be almost completely non-ionized or very less polar, while at 6 pH its retention will be significantly lower because the functional group will be almost completely ionized, that is, it would be more polar. Vice versa is true for basic analytes. The relative retention times of analytes can also be altered by changing the eluent pH to achieve efficient separation. Similarly, in reversed phase separations, the mobile phase is more polar, that is, it is highly hydrophilic as compared to the stationary phase. Mobile phase comprises of a mixture of water and an organic solvent, usually methanol or acetonitrile. The choice of organic modifier depends upon the properties of solvents such as dipole moment, acidity and basicity. For example, acetonitrile has a higher dipole moment and is more acidic, whereas the methanol has a lower dipole moment and is more basic, and it has a slightly lower elution strength. Different binary and ternary mixtures of these solvents with water can produce a wide range of polarity options for separation of compounds of different natures. Solvent mixtures may be isocratic, having fixed ratio of organic to aqueous components, or they may be eleotropic for gradient elution, whose strength can be gradually increased by increasing the amount of organic modifier. Here is an example of a reverse phase gradient elution in which the mobile phase composition and thereby polarity is changed gradually during the separation process. The two components of the mobile phase here are termed A and B. A is the weak solvent such as water or an aqueous buffer which elutes the analyte slowly. B in the figure is the strong organic solvent miscible with water such as methanol, isopropanol or acetonitrile, which rapidly elutes the analytes from the column. Precautions in usage of mobile phase. Only HPLC grade solvents are recommended to be used as mobile phases in HPLC. The solvent should be made homogeneous by proper mixing and filters should be used in reservoirs. Degassing helps to prevent the bubble formation in solvent as it flows through the column. If buffer solutions are used as mobile phases, thorough washing should be done using water to prevent any deposition of crystalline compounds. While performing gradient elution, The changeover of mobile phase polarity should be gradual and washing should be given using the solvent of intermediate polarity. Finally, the delivery of mobile phase into the column should be non-turbulent. Solvent delivery system. The solvent delivery system is an essential component of HPLC. It is meant to deliver the mobile phase to the column with a constant and pulse-free flow. The efficiency of the system and reproducibility of retention time is directly affected by the flow rate. Therefore, the solvent delivery system should function with high precision and accuracy. This requires the capability to maintain high pressure high enough to force the solvent through compactly packed column. Also, if mixture of two or more solvents is to be used as mobile phase, then the solvent delivery system should be able to mix all solvents together to give appropriate polarity. It should have low internal volume to facilitate fast mobile phase changeover with a minimum of mobile phase volume. The components of a solvent delivery system in an HPLC are solvent reservoir, pump, degasser, mixer and dampener. Solvent reservoirs are provided to store the mobile phase. These are usually made of glass. The mobile phase may be a liquid of single composition or a mixture of different solvents. If it is a mixture, it may consist of polar and non-polar solvents mixed in variable proportions depending on the composition of the sample. Therefore, the solvent delivery system in HPLC consists of a single reservoir or multiple solvent reservoirs. To facilitate the solvent flow under high pressure, valves are provided. These valves also allow rapid refilling of the solvent reservoirs. Degassing the mobile phase. Degassing is an important action performed prior to mobile phase delivery into HPLC system. Solvents remain in contact with the atmosphere and therefore essentially consists of an equilibrium level of dissolved air. When solvents are mixed, bubbles are formed due to dissolved air, which can interfere with the pump operation and sensitivity of detectors. Also, the solubility of analytes in air saturated solvents is lower as compared to the pure solvents. Degassing of the solvent before its entry into pump can resolve all these issues. The three processes adopted for degassing of mobile phase are sonication, vacuum filtration, helium sparging, as well as the membrane used for mobile phase degassing. When pure solvents are mixed to make up the mobile phase, excess dissolved gas escapes from bubbles because air is less soluble in solvent mixtures than in pure solvents. Bubbling can be prevented by keeping the mobile phase reservoir in an ultrasonic bath. The ultrasonic sound waves make the small bubbles to coalesce and allow them to escape easily. The excess gas is allowed to escape before it enters the pump. Therefore, the sonication degassing is done for pre-mixed mobile phases. It is not suitable for online mixing systems in which bubbles form inside the HPLC system. It cannot reduce the dissolved gas below the saturation level of the pure solvent. Another degassing system of mobile phase is vacuum filtration. In this technique, the solvent is filtered through a membrane under vacuum. This method can be easily combined with sonication of the mobile phase to remove both dissolved gas and particulate contamination. This technique works for pre-mixed mobile phases but is not recommended for online mixing. Since the mobile phase immediately begins to re-equilibrate with air, this technique is useful only for one-time degassing. Degassing of mobile phase by helium sparging. In this technique, a stream of helium bubbles is passed through the solvent which sweeps dissolved air out of liquid. helium is virtually insoluble in most HPLC solvents, so very little helium replaces the air. Helium sparging is very effective as it can reduce the dissolved air in common solvents to levels below the saturation level of mixtures. Helium sparging is thus especially suitable for use with online mixing systems. The only drawback associated with this technique is that the mobile phase composition may change slightly by selective evaporation of more volatile components in the solvent. This can, however, be prevented if helium is not supplied under excessively vigorous flow. Degassing of mobile phase through membrane. Online membrane degassing is the most convenient approach for solvent degassing. It consists of a hollow fiber made up of semi-permeable membrane through which the mobile phase or solvent flows. A partial vacuum is maintained on the outside of the membrane. The principle is simple. Since air can diffuse through the membrane but solvent vapors cannot, the dissolved air is removed from the solvent before it reaches the pump. The membrane degassing module is installed immediately upstream of the pump into the inlet line, so that redissolution of air into the solvent can be prevented. High pressure pump. A high pressure pump is enabled to aspirate the solvent or mobile phase from the solvent reservoir and forces it with pressure through the injector, column and detector. The mobile phase has to pass through the stationary phase inside the column, which may consist of a compact bed of adsorbent material or ion exchange resin or a microporous packing material. This requires appropriate pressure to force the mobile phase through the compactly packed column and at the same time dissolve the analytes. The pump efficiently provides the operating pressures ranging up to 6000 psi, sufficient to overcome the resistance to solvent flow through the column. As the solvent flows through the column, the components of the sample mixture equilibrate with mobile phase and the stationary phase and eventually separate on the basis of their solubility in the mobile phase. This equilibration requires sufficient time to occur that depends on the flow rate of the mobile phase. If the flow rate is too high, the analytes do not get enough time to equilibrate and may get eluted out from the column without separation. Conversely, if the flow rate is less than optimum, elution may take very long time. The separation of compounds is analyzed through peaks appearing in a chromatogram at characteristic retention time. The retention time is strongly influenced by the flow rate, composition and volume of the mobile phase. The flow rate of mobile phase is a critical factor that directly affects the retention time and peak height in the chromatogram. Van Demeter plots are often used to adjust appropriate flow rate for maximum efficiency of separation. The reproducibility of the chromatogram thus depends on the precision and accuracy of the flow rate. Therefore, the pump system should be capable of delivering a wide range of reproducible flow rates, commonly ranging from 0.1 to 10 milliliter per minute with reproducibility of 0.5%, and to cope up with the back pressures that arise due to the fluid flow. Appropriate adjustment of flow rate enhances run-to-run reproducibility so that the chromatogram of sample can be analyzed with respect to the one of standards or calibrants. There are several types of pumps that are employed in HPLC. The constant pressure pumps are connected to a low pressure gas cylinder and operate via gas pressure. The gas pressure is used to drive the pistons that further produce a consistent and continuous high pressure liquid flow. The solvent flow stops during the return stroke of pistons, therefore pulse damping is required to suppress the detector signal at this time. Syringe type pumps. These are suitable for small bore columns and have limited solvent capacity. These are operated by an electrically driven lead screw arrangement that moves a piston, which in turn generates the pressure enough to deliver a fixed volume of solvent to the column. The flow of solvent is pulseless and constant and is not affected by column back pressure and viscosity changes. Therefore, these pumps are relatively reliable. Their drawback is that due to their limited solvent capacity, that is approximately 250 milliliters, solvent needs to be changed often and gradient operation cannot be accomplished. Another type of pumps are reciprocating piston pumps. These pumps, through reciprocating motion of a piston within a hydraulic chamber, a motor electrically drives the piston back and forth. During the backward stroke, the piston sucks in the solvent from the reservoir, and during the forward stroke, it delivers the solvent into the column. The check valves are enabled that close the column outlet while aspirating the solvent in backward stroke and close inlet from the reservoir during forward stroke. Flow rates can be fixed by adjusting the piston displacement. These pumps are advantageous because their solvent delivery is smooth, constant flow rate can be achieved even at high pressure, and supports gradient operation. There is no limitation of reservoir size or operating time. In case of minor pressure pulses, dampening may be required. Mixing of solvents in HPLC. The solvent delivery system must be capable of mixing solvents homogeneously and vary the polarity of mobile phase gradually. In an isocratic mode, the solvent composition is kept constant throughout the chromatographic run and the analytes elute out when a fixed volume of mobile phase volume has transited through the column. However, in a gradient elution, the mobile phase composition is required to change over the course of chromatographic run. Also, the viscosity of the mobile phase may change due to change in its composition, and the pressure may be required to be adjusted to maintain the required volumetric flow rate. The pump that delivers the mobile phase can also be used to mix or blend the solvents. Pumps for mixing of solvents. On the basis of automatic mixing of solvents, there are three types of pumps. Binary pumps, these pumps mix two solvents together. Ternary pumps for mixing of three solvents together, and quaternary pumps that mix four solvents. This is a quaternary pump. It is most common in HPLC system and is able to mix four solvents efficiently in desired proportion with the help of a proportionating valve. Types of solvent mixing processes. The mixing of solvents to prepare appropriate mobile phase can be done in any of the three ways. Firstly, manual mixing. It is the simplest way of mixing solvents in a precise manner without using the pump. Low pressure mixing. This is done by using a single pump with a proportionating valve to deliver the solvent. And high pressure mixing. In this system, two pumps are used to push the solvent separately and the output liquids are blended by online mixing. High pressure mixing pump. The high pressure mixing system consists of two high pressure pumps, one for each solvent reservoir, and mixes the output of both to control the mobile phase composition. Essential features of solvent delivery system. The solvent delivery system is desired to have a low system volume so that the mobile phase changeover may be done rapidly with minimum volume. This is important in HPLC, firstly while using gradient mode and secondly while optimizing a separation process. In gradient elution mode, the volume or time required for the gradient to pass through the HPLC system is known as system volume. In a chromatographic process that employs a mixture of two solvents as the mobile phase, Initially, both the solvents are discharged from the reservoirs separately and are mixed in a desired ratio before the mixture enters the column. The system volume refers to the actual fluid volume from the point the solvents are proportionated. In other words, it is the volume between the point where the gradient is formed and the column inlet. It is also known as the delay volume or dead volume and affects reproducibility of gradients and throughput of a gradient separation. It also impacts the transfer of a gradient method from one system to another. The solvent delivery system in HPLC should be able to maintain the gradient volume at least equal to the gradient delay volume plus the column void volume. Pulse dampener. The solvent delivery system in HPLC is essentially required to deliver smooth pulse-free flow of mobile phase through the column. Pumps often deliver a series of pulses in the flow of mobile phase. Pulse flow of solvent influences the equilibrium distribution of analytes between stationary and mobile phase and affect the reproducibility of retention time of analytes. A stable baseline can be obtained in a chromatogram by controlling the pulses. Most of the detectors, particularly refractive index detector, are quite sensitive to pulses in the solvent flow and gather background noise which is reflected in the chromatogram. Thus, elimination of pulses also enhances precision and detection limits for trace compounds in a sample. Pulse dampener. Pulses in the flow of mobile phase can be eliminated by using dampeners. The simplest dampener consists of a large coil of narrow bore tubing placed between the pump and the injector. When the pulsating flow is encountered by the dampener, the pressure rises in the tube and the tube is stretched. Due to stretching, the volume of tube increases, which adjusts the excess mobile phase, thus lowering down the pulsation. The tubular coil flexes on each stroke of pump and absorbs the pulsation energy. As the pressure decreases, the volume of tube also decreases. Whole system works as a hydraulic accumulator and shock absorber, smoothing out the pulses in the mobile phase flow. So students, now let us summarize what we have learnt in this module. The composition of mobile phase to be used is selected on the basis of nature of analytes. The flow rate of mobile phase is a critical factor affecting the efficiency of separation in HPLC. Mobile phase delivery system is used to continuously deliver the solvent into the column with smooth and constant flow rate. Efficiency of analysis and reproducibility of results is highly dependent on performance of the solvent delivery system in HPLC. Thank you.